an image of a projective variety is again algebraic. Even projective if you, yeah. So today I will prove that we can also look at dimension of the fiber. So if you consider the function, like you have x goes to y, you consider dimension of the fiber, or y goes to x, as it was. The dimension of, so this is phi, of yx, which is by definition phi minus 1 of x, where x is a point in this x big. This is a function on x. Yeah. Yeah, sorry, this we take dimension of yx as a function of x. F of x is dimension of yx. Well, there could be 0 or non-zero, for instance. And what I will tell you today is that dimension, let's f, the set of all x such that f of x is bigger or equal than k is closed. Zariski. Of course, if you put k, let's k bigger, if you put k equals 0 here, you would obtain precisely what we had last time. But to do that, it takes some very pretty numerical arguments. So I would start with Hilbert function and Hilbert polynomial. So definition. Let me just maybe do it here. Definition. We take A star as a graded ring. And M star is a graded A star model, finitely generated. Okay, so what does it mean, graded model? This means that your C star action, which defines you the grading, is compatible with the multiplication by elements of A. So this means that A k times M L belongs to M k plus L, precisely as it works with multiplication within A. Okay, then H M of n, it's called Hilbert function, is equal to dimension over C of Mn. Here I assume that A is finite type. This, for the present purposes, this means that dimension of A k is finite. Dimension of A0 is 1. So this is just a Brown field. And then I would also assume that A for negative numbers is 0. This is assumption which we had for the graded rings of projective varieties. So this is natural assumption. Now we define Poincaré series. So this is Hilbert function, Poincaré series is Pm of t is equal to the sum from I equals 0 to infinity, t power I, P H M of I. So for typical example is we can take a star is equal to m star is equal to c of t, just polynomials with the standard grading by the degree, then hn of m star is equal, hm of n is equal to 1 for all n starting with 0, and Pm of n of t is sum from I equals 0 to infinity, t power I, or what is the same, 1 divided by 1 minus t. Clear? Good. We shall see more examples now, later. Okay, now the main theorem which I want to prove now is quite nice result theorem. So suppose you have P m of t, Poincare series. I work in these same assumptions as here, as above. Then Pm of t is Q of t. Okay, another assumption which I would have to make here is that A star generated by A1. This is, you can prove it, I mean, there is a version of this theorem without this assumption, which I'm not going to state or prove. You can do it as an exercise. It's not hard. T1 minus t power k, where q of t is polynomial. In fact, it's polynomial with integer coefficients. Clear? Okay. So this is the definitions. So proof. Okay, we can start. I mean, here it's step 2, but let's start with a simple example where well, I use induction by dimension of A1. So suppose that A1 is just empty. Then A star, because everything is generated by A1, is just C. This is our assumption. A0 is one-dimensional. So it's only ground field. And then this means that M, I mean, this means that M is finitely generated over A. So it is fine-dimensional. It's a vector space. Then HM of n is equal to 0 for all n except finitely many. For almost, well, except finite number. And then, obviously, this means that our Pm of t is a polynomial. Clear? There's nothing to prove. Okay, now this is the heart of the argument. I will consider operator Lx of m is equal to xm. So this operator x belongs to A1 non-zero. This operation of multiplication by m. So if you have m, you write an exact sequence. M goes to m, like mn goes to mn plus 1, right? Here you have C n plus 1, 0. And here you have K n 0, where Kn is a kernel of Lx, and K star. And C star is an image of Lx. These are two models, obviously finally generated, over our ring A. And this is an exact sequence. However, if you have an exact sequence, these find dimensional vector spaces. So this gives you, you can sum up dimensions and obtain 0 if you do it with signs. For instance, if you have short exact sequence, then the middle group has dimension which is equal to the left and sum of the left and the right. And the same is true for any long exact sequence, which you can just split on two, direct sum of exact sequence of three. Well, it's obvious. So what you have is dimension of, what is the sign? Dimension of Kn minus dimension of Mn plus dimension of Mn plus 1 minus dimension of Cn plus 1 is equal 0. Clear? Am I doing very slowly or? Okay. Questions? Oh, of course. Thanks. Did I say image? I think I said co-kernel, but I wrote image. Thank you. Yeah, I'm stupid. Anyway, so now, should I explain this? This is sort of easy because, okay, you take K, you take the image of K here, and you split M into direct sum of this image and the rest. You obtain a short exact sequence, and your K cancels this, and then for short exact sequence, this is clear. Okay, but then this gives you something. This equation gives you something about the Poincare series. Namely, you take P so this is H of n. This is Hm of n, Hm of n, Hm of n plus minus 1. Is it minus or plus? I'm always confused. Yeah, plus, of course. Here you have Hk of n, and here you have Hk of n plus 1. Now, if you take the Poincare series, T times P m of T is equal to sum T power n H n minus 1 m of n minus 1. All right? I just multiplied everything. And then this gives us 1 minus T. Well, let me do it like instead of n, I would write n plus 1, and here I will have n. Then it becomes even better. Or, well, we're in, yeah, right. Anyway, 1 minus T, Pm of T is equal to Pc of T minus T Pk of T. You just use this shift.
Professor, please turn the monitor.
Thank you. Okay. And this gives us Pm of t equal to P C of t minus T pk of t. Now, both C, so this is step 3, C star and K star are models over. So if you multiply any element of C by X, it becomes 0 because it sits in the kernel. And if you multiply element of K by X, it becomes 0 because it's co-kernel. And if you multiply, you can take this element, you take its pre-image, you multiply it by X here, and you put it there. Since it's co-kernel, it becomes 0. So there, are A quotient by the ideal generated by X models. Okay, using induction, we can assume that these guys, the theorem is true for C and K. This is because we know it for 0. This was step 1. So we start induction with 0, and we want to obtain it, the same result for this is divided by 1 minus t. Okay, this is polynomial divided by 1 minus t in some power. This is polynomial divided by 1 minus t in some power. Then this fraction is again polynomial divided by 1 minus t in a bigger power. This finishes the proof. The same is true for M. Am I clear? Questions, comments? Did you know that already?
Do the exponent of the denominator of the BC star and BK star needs to do the same exponent? Because
it's plus 1 actually. But then this polynomial can, in fact, it can be smaller because at some point you can have cancellations. But it's no bigger than n plus 1, definitely. With then dimension of A1. Okay, now I want to give you a certain silly combinatorial expression. I mean, there are billions of combinatorial expressions for binomial coefficients. This is one of them, so it's sort of useful if you want to express. Okay, so lemma (1 minus t power n) minus what? Minus r. Minus r is sum t power k from k equals 0 to infinity. And here you have binomial coefficient r plus k minus 1. And here r minus 1. So the good thing that this is actually a really polynomial is something quite useful. We shall use it later. But so how you do that? You take derivative. So 1 minus t minus r d by dt is equal to, obviously, r times 1 minus t power minus r minus 1. This is obviously true. Well, I use this convention. Then this is obviously true for r equal 1. Well, for r equals 0, r equal 1, this is obviously true. Then I would just take derivatives, both sides of this equation, and check that this becomes this, and this should become r times the same series from k bigger, from r instead of r plus 1. Okay, so let's take derivative. Have you seen that already? Who knows this?
This is actually a generating function for a number of monomials of degree r and
precisely.
variables.
Precisely. This is why it is useful. Okay, then I would just skip this computation, which is simple. I mean, you just take the derivative by k. K becomes k minus 1, and you have coefficients of k. Then you renumber. L becomes k minus 1. You obtain very similar expression for L, except now you have k L minus 1 disappeared. Then you write this as using the formula for binomial coefficients. L plus 1 cancels this L plus 1. You obtain this fraction of factorials. And then you realize that if you multiply it by r, I mean, you will obtain binomial coefficient. That's all. There's nothing much to do. And then you denoted this guy by Vt, Vr of t. This is right hand side of this. So we obtain that dv r of t by dt is equal to r v r plus 1 of t. And the same is true with this d 1 minus t power r minus r by dt is r by the same r minus 1 minus r minus r minus 1. Okay, so for v0, v1, you have vr equal to 1 minus t power minus r of t. You take the derivative, you obtain the same for r plus 1. This just cancels, and you obtain the same equation for that. And then you use induction by r. And you obtain this combinatorial identity. Good. The important, why are we interested in that? This is because Poincare series, the coefficients are in fact polynomial. Well, not quite, because they start being polynomial starting from certain point. So for a while they're not polynomial, but for sufficiently big numbers they're polynomial. So theorem, again you have a star finite type. A star model, finitely generated A star model. You define, then there exists n sufficiently big such that, and a polynomial, and polynomial p m of hm of t such that such that this Hilbert function of n is equal to the polynomial m of n for all n sufficiently big. So proof. Of course, it's a theorem about this kind of functions. So we need to show that r plus k minus 1 by r, the binomial coefficient, minus 1, this binomial coefficient is a polynomial of k in k. This is clear. I mean, you just expressed it as usual, and you notice that this precisely for sufficiently big well, since the coefficients we have also minus I here and minus minus I here. This is polynomial on k if r minus 1 minus I is bigger than 0. Because this is it has degree r minus 1. Why it is so? You look doubtful. Okay, they will write it as usual. That this binomial coefficient is equal. You take on the top. You take the product of. So this is equal, obviously, r plus k minus 1 minus I divided by r minus 1 factorial times k minus I factorial, right? Okay. Now we cancel the first k minus 1 minus I terms. This gives us, here you have r minus 1 factorial, and here we have, we start with k minus I plus 1, then k minus I plus 2, and so on, up to r plus k minus 1 minus I. Okay, this is precisely r minus 1 terms. So it is a polynomial. Okay. Now we write this expression for Poincaré. So this is this expression. So this is okay. Poincaré series for m is q of t divided by t 1 minus t power r. This is equal to the sum ai t power I. This is q of t is ai t power I. And then you multiply it by this formula, t power k minus I times r plus k minus I minus 1. Here I have r minus 1. This is all terms under k, under t power k. And they're all polynomial for k, which satisfies this condition. Something is wrong here, or maybe not. So it should be k, of course. K minus 1 minus I positive. OK. But there are finitely many of these terms. So after you start with k, which is sufficiently big so that this number becomes positive, you obtain polynomial by this argument. OK. And this obviously happens because, for instance, you can consider the following nice A model. So let me give an example. We take M A star, again polynomial ring. Then you take M star, Mi is AI plus D. Then H M of N is equal either 1 for I for N bigger than or equal to D, or 0 for N equal less or equal to D. So you see, you start with 0, 0, 0s, then you go 1, 1, 1, 1, 1. This is polynomial, but polynomial only after a certain after n sufficiently big. I mean, constant is a good polynomial. There's nothing bad in that, but of course, you have to take sufficiently big numbers. And now I can give you a definition. Hilbert polynomial of variety. This is very important. When you do algebraic geometry, you see these Hilbert polynomials all the time. So definition, you have or a ring, you have or a model, you have M star, A model, A star model. Then P M star of T polynomial defined in this theorem. Then Pm star of T is called Hilbert polynomial of M star. And the important special case is if A star is a graded ring of projective variety. So what we can say about this graded ring? First, it's finite type, right? Because for each degree, for each grade, for each degree, the AK is just a quotient of polynomials of the same degree, which is finite-dimensional space. A0 is again a quotient, so it's just constants. And finally, everything is generated by A1 because it's true for polynomials. Then the corresponding P A star of T is Hilbert polynomial. So it's variety X is Hilbert polynomial of X. Questions, comments? Yes, please.
Why is unique generated by A1?
Because A star is a quotient of polynomial ring Z1 dot 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 or Z0 dot dot Z some n, quotient by I star, and this is already generated by A1. So then the quotient is also generated by the same generators. Did I? Okay. So let's compute some examples of Hilbert polynomials. So the first example is just what is the degree of the Hilbert polynomial? It's not example, it's just trivial observation. So claim. Okay, so you have P. You have first you start with the Poincare series. Yeah, it's H. Sorry, it's H. Of course, I denote this H, and P is Poincare series. Pm of t is equal to Q of t divided by 1 minus t power d. And I assume that Q of 1 is non-zero, then you can't, I mean, this is not, I think it's called a reducible fraction. You cannot factorize it more. Okay, then degree of the Hilbert polynomial is equal to d minus 1. Okay, proof. And now I unfortunately erased the formula, but we used to have it. So on the previous slide. So H Hilbert polynomial is the sum of several terms, which are all obtained, I mean, up to a constant. They are proportional to n minus is a sum of, here you have n minus I plus 1. You multiply it by n minus I plus 2 and so on, and up to n minus I plus d minus 1. This is what we had on the previous slide. I can show you if you don't believe me. It's not hard. Okay, the degree is equal to n d minus 1. Because there are precisely d minus 1 terms. Right. Yes?
Isn't it strange? If d equals 0, then the degree is minus 1?
Yeah. Yeah, this we start with n very big.
I mean, if d equals 0, then the degree is...
Yeah, we should assume that they're all positive numbers. This assumption on the previous slide.
But d can be 0, right? D. The small d.
It doesn't make sense. Well, you can probably do that, but you would say that, okay, well, it's a question, what is degree of 0? Who cares? I mean, you just set it to 0 and forget it. Okay, so this is this polynomial. Okay, now let's compute it for polynomials. I will compute the Hilbert, the Poincare series and Hilbert polynomial for polynomials. Okay, so example. If you have A is polynomial ring, x1 dot dot or z1 dot 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 up to z d. Again, the grading is standard by degree. Then h A star of t is 1 minus t power t, or d minus 1 minus d. And then okay, here you have obvious misprint. Hilbert polynomial P A of t is d minus 1. Okay, so the second follows from this and this observation, right? So need only to show this first, the first. For that, we just write exact sequence in that particular case, and we realize that when we multiply by x, there are no kernel. So you have A0 goes to A star, goes to AD, goes to AD plus 1, and then you have the co-kernel, CD plus 1. Okay, so what is the CD? The co-kernel, CD C star. You take polynomials up to polynomials which are divisible by xd, for instance, by zd. By the last, this is just polynomials on the first variables. So this is c of z1 dot dot dot. Here I multiply by zd for up to zd minus 1. Okay, and then you can use induction. Because this is obviously true for, say, for one dimensional, this is obviously true. I mean, when this is something which we already did. So h c of t, well, c of z of t is equal to 1 minus t power minus 1. And then each time you add a variable, you obtain that h a star of t times 1 minus t is equal to h c star of t. This is by induction already 1 minus t power d minus 1. So this is 1 minus t power d. Am I clear? Okay. One of the important applications is of Hilbert polynomial is that its degree is more or less dimension. Well, if we work with cones, it's precisely dimension. If we work with the projective variety, it's dimension plus 1. So theorem, we have A star graded ring of projective variety. X inside CPN. And then degree of its Hilbert polynomial h a star p Hilbert h a star of t is equal to dimension of x minus 1. This is I mean, we had 3 definitions of dimension. This is the 4th, and it is quite useful, except that so far it works only for graded things. If you want to do it for non-graded, you have to do more commutative algebra, which people usually don't. Okay, so proof step 1. So you have M star finally generated by generators of degree S1 dot SR. Then this is M is a quotient of a free model. But you know what is since the free model is direct sum of free one-dimensional models, you know what is their Hilbert polynomial and Poincare function. And this gives that HM star of n is less or equal, is bounded by the Poincare, the Hilbert functions for this model shifted by Si. So it's sum from I equal 1 to R HM star of n minus Si. Okay. So what will happen if you take a polynomial and shift it by certain numbers and add up together? Degree doesn't change. So degree, well, the only problem is, of course, that this is inequality. So, but then you have degree of M HM is less or equal than degree of A HA. Right? So we have a bound in one direction. The idea is that I would just deduce everything from what I already know about polynomials. I already know what is degree of Hilbert polynomial for polynomials. And we will use it to deduce. So step two, if A star is contained in B star, and B star is a finally generated A model, then you have an equality in the opposite direction, and degree of HA of T is equal to degree of HB of T. Am I clear? Okay. And this implies a nice thing, that if you have a morphism from C of X to C of Y, well, the morphism of graded rings preserving grading is precisely as morphism of cones, C star invariant morphism. And then suppose it's finite, so that this is finite generated model over that, and dominant. So that this is contained in the ring of functions on there is contained in the ring of functions there. Then you can apply, you can consider A as functions, regular functions on there, B as regular functions on there, and apply this argument. And you obtain that Hilbert polynomial of C of X has the same degree as Hilbert polynomial of C of Y, where I consider, well, I should probably write HO of C of X, and here I should write HO of C of Y. And I consider these two as graded rings with the grading which is induced by, I mean, it's a cone. It has this direction. Okay. Okay. Now I want to apply Noether normalization theorem. Of course, lemma, it takes some work because we can't directly apply it to a cone because cone is not affine. It's without zero. So, but you know, the people usually confuse. They call both. You can add zero, and it will be cone, or you can not add zero, it's still cone. Just people call both things cone. I would just use I would call them cone. I will just use different notation. So step 3, take C plus of x is just C of x union with 0. This again, it's affine C star invariant variety in C power something n plus 1. And the same as with I. Okay, then we can apply Noether normalization. Normalization implies, we assume that C plus of x belongs to Cn plus 1 for general projection from Cn plus 1 to C d, where d is dimension of C plus of x. This is pi. Then you take pi from C plus of x to C d, and it is finite and dominant. Right? This is something which we already had. Good. Then degree of the corresponding OCD. Of course, this is D, right? This is something we already proved. The degree of grade functions on XD is D or D or D minus 1. D minus 1? Okay. D minus 1, I'm always confused. D minus 1. And this is by the previous step, step 2. This is the same as degree of Hilbert polynomial. So it's degree of Hilbert of OCN, degree of Hilbert of OC plus of x. But this is the same as dimension of, they have the same dimension, so it's dimension of OC plus of x minus 1. Okay. Finally, we got what we wanted. So dimension, at least for then degree. No, I think it's, yeah, degree of Hilbert polynomial of any cone is equal to dimension of this cone. There's something bad with minuses. I think here it should be, yeah, it should be plus 1 probably. So it's dimension, so it's first it should be cone, dimension of C of m. So when dimension is 1, this is 0. So it's minus 1. Okay. Here you have minus 1 as well. Am I clear? Good. So what we did, we just used projection. We noticed that this projection, the dimensions are the same, and the Hilbert polynomials are the same for both. The degrees of Hilbert polynomials are the same here and there. So here, the Hilbert polynomial has the same. Here, this relation is satisfied. Then it has to satisfy there. And finally, we need to reduce everything to the case where of projective variety. But then step 4, dimension of C plus of m is dimension of m plus 1. This is because C plus of m is fibered with one-dimensional fibers. Generally, for general point, of M, which is smooth, this is just a product locally. So the dimension is clearly here for the cone is bigger by 1 than the dimension of here. And then the degree of Hilbert polynomial of M is equal to dimension of M by this formula. Well, something, there is one which is missing here or there. So it's, if this is, say, one-dimensional, then this is 2. So you have +1. Good. Please check the ones. I mean, I'm sort of lost with they keep disappearing and reappearing. So please check that carefully. But you can always see just on CP1, and you will see that every time you can add 1, you just look at what happens with CP1 and you add it. It's not hard. OK, so let's maybe have a break until 14:34. And then I will continue with the rest. Have 5 minutes break. If you have questions, please ask. Yeah, and I would probably leave it here. So there's this notion of from topology, which is generalization of the continuity. And it is defined very abstractly, the same way as continuous functions, which is semi-continuity. But unlike with the usual continuous function, which is a map from topological space to topological space, semi-continuous functions are maps to R. You can do that with any ordered topological space, but it doesn't make sense, probably. Definition. So first you have, if you have a sequence, xi, sequence of points in X, then a limit set of, so it's lim of xi, is a set. It's an intersection of closures of x n, xn plus 1, and so on, for on n. So you take, this is the same as you take, it's a point such that any neighborhood of this point contains infinitely many points in this sequence. This is the same. So if you have a point which has such property, then it is contained in this closure, and conversely, it's the same. OK, now, so it's a set. OK, limit superior is supremum of limit of x. So we take for each subset x a inside R, lim sup, or for each sequence x I inside R, lim sup of xi is supremum of limit of xi, and lim inf, limit inferior of xi is inf of lim of xi. This is standard in analysis. Okay, now definition. Phi from X topological space to R, upper semi-continuous. So the limits should jump. For upper semi-continuous function, the limits jump. This means that for each x inside the limit of xi, of the sequence xi, phi of x is bigger or equal to lim I think there's an error here, lim inf of phi of xi. Oh no, lim sup, of course. Sorry. So let me explain that geometrically. This means that you have a sequence. It has many limit points. You evaluate your function in these limit points, and it should be bigger or equal than limits of the values evaluate a function phi of xi. So the usual continuity means that you evaluate on limit, it is the same as function, it belongs to the limit. And now it should, no, okay, of course inf.
So
yeah.
Is it just the upper semi-continuity is just an ordinary continuity, but with respect to the different topology of narrow?
Yeah, you can define topology. It's called Scott topology.
Generated by semi-infinite intervals.
Yeah, something like that. But I don't. I think I gave it at some exam, and nobody could solve it. So it's complicated. Okay, so now I would give you example. This is the basic example which you should consider. Example of upper semi-continuous function. It's called Rydrom or Riemann function. Raindrop. So raindrop is because, okay, you listen to rain. It's very it goes tuk 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 tuk, and then for bigger intervals of and for even bigger it's louder. So it gets less louder and faster and faster. I mean, it beats very slowly and loud, and it beats quiet and fast. So phi, it was denoted here xi from R to Q positive. It takes a xi of irrational, it's just 0. And xi of P over Q is equal to 1 over Q for irreducible fraction. P Q irreducible fraction. You see, you go to the special point, the limit jumps. But if you, it can be smaller in the sense that if you have any sequence of rational number which converges to 1 over Q, then it has to be, well, it can't be, the denominators can be less than Q. So it can't be bigger. Okay. So this was semi-continuity. Now, this is what your Dima was asking about the pre-images. So claim. phi from X to R, X topological space. Then phi is upper semi-continuous if and only if phi minus 1 of this of this race, phi minus 1 of from A to infinity is closed for all A. Okay, proof. It's almost elementary. So suppose it is phi semi-continuous, semi-continuous, and then you have xi, a sequence which belongs to phi minus 1 of A infinity. Then the limit phi of any point in the limit of xi is bigger or equal to than A, right? Then the limit set of xi of the sequence belongs to this phi minus 1 from A to infinity, and then it is closed. Because a closed set is precisely the set which such that all its limits are belong to it. Well, we should probably assume something like base is countable. So then the phi minus 1 of this guy is closed. Converse is very similar. So suppose that this preimage is closed. Then for each sequence of points in this, so conversely, if phi minus 1 from A to infinity is closed, then for all sequence xi such that phi of xi is bigger or equal to A minus epsilon, phi the limit of xi has the same property, is bigger or equal to A minus epsilon. Okay, so what is a sequence which converges to okay, so if you have a sequence, then if xi has property that phi of xi has limit of this is bigger or equal than A, this means that they all belong to these sets for each epsilon. Then xi belong to this phi minus 1 of A minus epsilon infinity for all epsilon, right? And then the limit has the same property. Phi of limit of xi is also bigger or equal to than A. You can geometrically imagine it as follows. You look at this raindrop function, and you consider all what lies below the graph. It's closed. This is another way of geometrically interpreting semi-continuity. We're interested in semi-continuity only for Zariski topology. And in fact, this is pretty much, I mean, you don't have semi-continuity almost anywhere except in Zariski topology. So it's the main application. And for Zariski topology, usually you have functions which take values in integers. And then the semi-continuity is very simple. So definition, constructible set in M, which is algebraic variety, is a set generated by Zariski closed unions, intersections, and complements. So you have three logical operations on sets. You generate. It has even a name. It's called the ring of subsets. Again, what is important is that intersection of closed is closed. So constructible is closed without closed. That's all. If you look how you, I mean, intersection of closed is closed, but yeah, finite. By finite. Did I say finite here? No, I didn't. I meant to say it. Anyway, union of finitely many closed is closed, intersection of closed is closed, and complement is open, and then you can use the standard, normal form to express all result of all such operations in that form. Okay. Now, proposition. I won't use much constructive sets today, but I just wanted to tell you this is an important notion. Proposition. So suppose you have semi-continuous function phi from x to z positive, semi-continuous, and x is algebraic with Zariski topology. Algebraic variety. Then phi has finitely many values, and for each t, phi, this level set phi minus 1 of t is constructible. Okay, so proof is very simple. You have A1 less than A2 less than A3 and so on. Then you have phi, let's call, is there any notation for that? Yes. Z AI is by definition phi minus 1 of the corresponding corresponding ray AI infinity. This is Zariski closed by semi-continuity. On the other hand, this gives you a sequence of embedded, monotonous sequence of Zariski closed subsets, which has to stop by neutrality. Then ZAI stabilizes. So ZAI contains ZA1, contains ZA2, contains ZA3, and so on, and stabilizes by neutrality. Well, to be honest, I didn't tell you. It should, when we define algebraic variety, we should have, it has to be, for instance, connected. If we have like infinitely many disconnected components, it won't work. So we assume that it is, say, connected, or even better, reducible, something, connected in Zariski sense, or finitely generated for each affine subset. Okay, and then phi, since it takes values in Z, phi of, like you have phi minus 1 of AI of A, for instance, is equal to Z A without Z A plus 1. Right? Because this it makes sense only for integers. I mean, you can do it for non-integer, but it will be the same. So it changes only if you start with integer for A equal and Z. If you start with integer, for the next time it changes, it will be A plus 1. Okay, so it's contactable. And now semi-continuity of dimensions. So claim you have x over y over x is a family of varieties. So family of varieties, if you recall, we had it last time, is just any morphism for each point x inside x. You take fiber, phi minus 1 of x is yx. This is a fiber of this element of this family or fiber of this fibration. And then dimension of phi minus of yx is semi-continuous, upper semi-continuous, as a function of x. Is the statement clear? This is something we have already done. So what happens is that you have 0 dimension is the biggest. I mean, dimension, this means that you have dimension, the set of all x such that dimension of x is bigger than A. This set, let's call it XA. Then you have x0 containing x1, containing x2, and so on. And these are all Zariski closed. They are finitely many. Okay, there's this, again, this notion of Macaulay matrices, which we had last time. Maybe I should continue from that point this Monday. Monday we'll have a class, right? Okay, maybe I have like 4 minutes. I can tell you something at least. This is just a reminder. So what you have is you have a graded ring and defined by an ideal. You have A star subset inside the polynomial ring. Generated by W1 WSR inside the degree D component. Then you have this matrix, which takes the space generated by, so W is generated by these guys, W1 WR, and you take W times monomials, Z0 Zn power S minus D, and this you just multiply them. This goes to C Z1 Z0 Zn power S. This is Macaulay matrix, and its image is precisely ideal. This is something which we had, right? Good. Now, what I claim that you have this A is polynomials quotient by I star. And then you consider the Hilbert function of this quotient. A of S, it is equal to the dimension of the C of Z0 dot Zn degree S minus rank of Mikhail matrix. So this is M of S, MS, minus rank of Mikhail. Is it denoted here MW, of course, WS, minus rank of MWX, S. All right? Because this is degree of dimension of the quotient, and this has the same dimension as that. Okay. Then HA of S is upper semi-continuous. Semi-continuous as a function of x inside x. So you evaluate that at every point like we did last time. So how I prove that? Okay, suppose that the rank is equal R, for instance, or W. Suppose that rank is equal to W. This means that you have a minor W by W in that matrix, which is non-degenerate, like submatrix of dimension W by W. We deform this a bit because everything depends smoothly on a point X, and it remains non-degenerate. This means that the set where rank is at least rank of the matrix is at least W is Zariski open, and then its complement, which is the complement of the set where minors W times W minors are non-degenerate is Zariski closed. But this is precisely the set where this has dimension bigger than the difference between this and W. Okay. So we obtain that this is semi-continuous. I think I would have time to finish. Now let's prove that the degree, so claim degree of Hilbert polynomial of this A of T is upper semi-continuous as a function of X. Okay, it's easy. The point is that you can express. Is it okay if I take extra 5 minutes? Just because next time I don't want to repeat everything. So degree of h of t is equal to logarithm h of t by logarithm of t limit by t goes to infinity. Right? This is true for all polynomials. Being clear? Okay. This is degree. But then you can write here h small, because for bigger t, they are equal. And then h small is already upper semicontinuous, and log even it's monotonous. So it maps semicontinuous to semicontinuous. Okay. And this is semicontinuous. And this is also semicontinuous. Okay. Now let's finish with the theorem of semicontinuity of dimensions. Dimensions, semicontinuous. So how you do it? Okay, so again, we have this like last time, the same, I just copy-paste, there's nothing new. So you have a subvariety, projective subvariety, which depends on a parameter. This means that you have z inside a product of x and Pn. X times Cpn. And you project it to x. So you have this projection from z to x. And then we consider the function of, like d of x is dimension of pi minus 1 of x. And I claim that I need to prove that it's semicontinuous. D of x, semicontinuous. Okay, so how we prove it? Well, we choose the generator. We notice that z has a generator. I mean, z has an ideal. Ideal of z is generated by w1 dot w r. We make these generators homogeneous of degree d, like last time, just by multiplying these generators by all monomials of appropriate degree. And choosing d is sufficiently big so that it's bigger than all of these degrees. Then what we obtain is that this set pi, let's call it zx. Zx is the ideal of Zx is precisely w1 of x dot 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 wr of x. And then its dimension is degree of its Hilbert, of the Hilbert polynomial of the quotient of the polynomial ring by this polynomials, which we consider just homogeneous polynomials now inside, like last time. So now it's homogeneous polynomial and polynomials in a polynomial ring. We take the quotient, we take a look at the Hilbert degree of Hilbert polynomial. It's the same as dimension of the corresponding variety, and it is semi-continuous. That's all. Thank you very much. I think I'm done. Finally, sorry. And yeah, if you have any questions, please ask.